At 0800 hours on March 15, 1943, a German Panzer V Panther tank rolled off the assembly line at MN factory in Nuremberg. The tank weighed 45 tons. Frontal armor was 80 millimeters thick, substantially thicker than American Sherman tank's 51 millimeters frontal armor. The Panther's armor was sloped at 55 degrees to maximize effective thickness. On paper, the Panther was nearly invulnerable frontally. But there was a problem the factory workers and tank crews would not discover until combat. The armor was brittle. It would crack under impact in ways that thinner Allied armor would not. The brittleness was not poor manufacturing. It was chemistry. German steel for tank armor in 1943 was alloyed with vanadium, tungsten, and nickel because Germany lacked adequate molybdenum. Molybdenum was the superior alloying element for armor steel. It increased hardness without sacrificing toughness. But Germany had no significant molybdenum sources. The world's molybdenum production was concentrated in one location, Climax Mine in Colorado, 10,500 feet elevation in the Rocky Mountains, 75 miles west of Denver. Climax Mine produced approximately 30 million pounds of molybdenum annually. During World War II, roughly 75% of world production. The remaining 25% came from scattered sources in Chile, Norway, and China, most of which were inaccessible to Germany. The United States controlled the molybdenum supply. American, British, and Soviet tanks used molybdenum-steel armor. German tanks increasingly did not. The metallurgical advantage was subtle but decisive. Allied armor absorbed hits. German armor cracked. Molybdenum is element 42 on the periodic table. Silvery white metal. Melting point 2, 623 degrees Celsius. Density 10.28 grams per cubic centimeter. It occurs naturally as molybdenite ore, molybdenum disulfide. The ore is found in porphyry copper deposits and as separate molybdenite veins. Climax Mine sits atop the richest molybdenite deposit ever discovered, a vertical ore body approximately 1,000 feet in diameter, extending over 3,000 feet deep into Bartlett Mountain. The deposit was discovered in 1879 by prospector Charles Center searching for gold and silver. He found molybdenite, but had no use for it. In 1879, molybdenum had no commercial applications. The mineral was worthless. Center staked claims anyway. By 1900, metallurgists had discovered molybdenum's properties as steel alloying element. Small quantities, less than 1% by weight, dramatically improved steel properties. Hardness increased, toughness increased, resistance to high temperatures increased. Molybdenum steel became valuable for high-stress applications. Mining began at Climax in 1918 during World War I, when molybdenum demand surged for armor plate and artillery barrels. The mine operated sporadically through the 1920s and 1930s as molybdenum demand fluctuated. In 1939, as war began in Europe, molybdenum demand increased. By 1941, after America entered the war, Climax Mine was operating at maximum capacity, producing approximately 30 million pounds annually, employing over 2,000 workers, operating 24 hours daily. The production was essential for American war industry. Every armor plate for every American tank contained molybdenum. Every armor plate for every American warship contained molybdenum. Artillery barrels, aircraft engine components, high-stress mechanical parts all required molybdenum steel. The United States consumed approximately 20 million pounds annually for military production. The remaining 10 million pounds went to Britain, Soviet Union, and other Allied nations through Lend-Lease. The metallurgy of armor steel is complex. Pure iron is relatively soft. Adding carbon creates steel, which is harder but brittle. Adding alloying elements modifies steel properties. Different elements produce different effects. Nickel increases toughness. Chromium increases hardness and corrosion resistance. Manganese improves strength and wear resistance. Molybdenum increases both hardness and toughness, simultaneously, a combination difficult to achieve with other elements. For armor plate, the ideal properties are hardness sufficient to resist penetration and toughness sufficient to prevent cracking. These properties are somewhat contradictory. Increasing hardness usually decreases toughness. Molybdenum solves this by increasing both properties together. Steel alloyed with 0.2% to 0.4% molybdenum exhibits hardness comparable to higher carbon steel, but retains toughness comparable to lower carbon steel. The result is armor that resists penetration while absorbing impact without catastrophic cracking. American tank armor in World War II typically contained 0.25% molybdenum. Sherman tank frontal armor was rolled homogeneous armor, steel plate rolled to uniform thickness, heat-treated to specific hardness, then bolted or welded to tank hull. The armor was 51 mm thick at 56 degrees slope on M4A3 variant. Effective thickness after accounting for slope was approximately 90. The armor was designed to resist German 75 meters anti-tank guns at ranges beyond 500 meters. Combat experience showed Sherman armor performed better than thickness alone suggested. German 75 mm rounds hitting Sherman frontal armor at ranges beyond 800 meters often failed to penetrate. When penetration occurred, the armor typically deformed rather than shattering. The deformation absorbed energy, reducing post-penetration effects. Crews in penetrated Shermans often survived because armor fragments were minimized. The molybdenum content contributed to this performance. The steel was tough enough to deform rather than crack. Soviet T-34 tank armor also used molybdenum-steel. Soviet metallurgists had studied American armor steel specifications and adopted similar alloy compositions. T-34 armor was sloped at 60 degrees more extreme than Sherman slope, with 45 mm frontal armor providing effective thickness of approximately 90 mm. The armor was hardened to high levels but retained toughness through molybdenum content. T-34 armor was renowned for deflecting hits that should have penetrated based on thickness calculations alone. Part of this performance came from extreme slope. Part came from superior metallurgy using molybdenum. British tank armor specifications also included molybdenum. Churchill tank armor, Cromwell tank armor, later Comet tank armor all used molybdenum-steel alloys based on American metallurgical research. Britain received molybdenum through Lend-Lease shipments from United States. British steel mills added molybdenum to armor plate production. The result was British tanks, with armor properties comparable to American armor despite different tank designs. Germany faced opposite situation. German metallurgists understood molybdenum's value for armor steel. Pre-war German armor specifications included molybdenum, but Germany had no molybdenum sources. Pre-war Germany imported molybdenum from Norway. After Germany occupied Norway in 1940, Norwegian molybdenum mines at Knaben provided limited production approximately 1 million pounds annually. This was insufficient for German needs. German steel production required approximately 10 million pounds annually for all military applications. Armor plate alone required 3 to 4 million pounds. German response was substitution. Metallurgists experimented with alternative alloying elements that might replicate molybdenum's properties. Vanadium was tried. It increased strength but decreased toughness. Tungsten was tried. It increased hardness, but was even scarcer than molybdenum and needed for cutting tools and armor-piercing rounds. Nickel was increased. It improved toughness, but decreased hardness. Chromium was increased. It improved hardness, but made steel more brittle. No combination of substitute elements replicated molybdenum's balanced effect. German armor steel from 1942 onward used whatever alloying elements were available in quantities that approximated desired properties. The compositions varied between production batches as element availability fluctuated. Some batches were harder but brittle. Other batches were tougher but softer. Quality control was difficult because optimal composition could not be maintained consistently. The Tiger tank illustrated the problem. Tiger Eye frontal armor was 100 mm thick vertical plate. The thickness provided protection against most Allied anti-tank weapons. But the armor was hard-faced. The outer surface was hardened to resist penetration, while the backing was softer to absorb impact. This worked when armor chemistry was correct. When chemistry was wrong, insufficient toughening elements, excessive hardening, the armor became brittle. Hard-faced plates would crack under impact, sometimes catastrophically. Combat reports from Eastern Front in 1943-44 documented Tiger tanks with cracked armor. Soviet 76mm rounds hitting Tiger frontal armor at close range sometimes caused cracks that propagated across entire plate. The cracks did not always penetrate, but they weakened armor structurally. Subsequent hits on cracked areas could cause plate failure. German tankers reported armor cracking from hits that should not have penetrated. Post-battle examination showed brittle fracture patterns indicating poor armor metallurgy. The Panther tank suffered similar issues. Panther armor was well-designed, sloped at 55 degrees, 80 mm thick frontally, providing effective thickness over a 100 mm. Early Panthers in 1943 had armor quality problems. Plates cracked under hits from Soviet 76mm guns. Plates cracked from non-penetrating hits. The impact energy caused brittle fracture even when shell did not penetrate. German metallurgists investigated and found inconsistent molybdenum content. Some plates had adequate molybdenum from Norwegian sources. Most plates had insufficient molybdenum and relied on substitute elements that did not prevent brittleness. The metallurgical problem was documented in German armor testing reports. Armor plates were tested by firing shells at them and examining results. Plates with molybdenum content above 0.2% exhibited ductile behavior, deforming under impact, absorbing energy, resisting cracking. Plates with molybdenum content below 0.1% exhibited brittle behavior, minimal deformation, crack formation, catastrophic failure. German armor production in 1943-44 was producing plates averaging 0.5% to 0.1% molybdenum below the threshold for optimal performance. The shortage forced German tank design decisions. If armor metallurgy was suspect, armor thickness had to increase to compensate. Tiger II tank frontal armor was 150 mm thick, nearly 3 times Sherman thickness. The thickness provided protection despite metallurgical deficiencies. But thickness meant weight. Tiger II weighed 68 tons, impractical for most bridges, difficult to transport, mechanically unreliable. The weight was partly compensating for inability to produce high-quality armor steel. American metallurgists were aware of German problems through captured armor samples. American intelligence collected Tiger and Panther armor plates from knocked-out tanks, shipped them to Aberdeen Proving Ground in Maryland for analysis. Metallurgical testing revealed German armor chemistry, hardness, toughness. The analysis showed German armor was harder than American armor, but more brittle. American metallurgists concluded German armor would crack under conditions where American armor would deform. The conclusion influenced American tank tactics, engaging German tanks at ranges where Sherman guns could crack German armor through impact stress rather than penetration. The molybdenum advantage also affected armor production efficiency. American steel mills could produce armor plate with predictable properties because molybdenum supply was consistent. Quality control was straightforward: add specified molybdenum percentage, heat treat to specified hardness, test for toughness. Reject rates were low. Production schedules were met consistently. German steel mills struggled with inconsistent alloying elements. Reject rates were higher. Production schedules were disrupted. The metallurgical uncertainty created production inefficiency beyond the material performance issues. Soviet Union received molybdenum through Lend-Lease, but also had domestic sources. Molybdenum deposits in Kazakhstan and Siberia were developed during the war. Production was smaller than American production, but sufficient for Soviet armor needs when combined with Lend-Lease supplies. Soviet metallurgists used molybdenum conservatively, specifying minimum percentages sufficient for required properties, not exceeding those percentages unnecessarily. The conservative approach allowed Soviet armor production to continue at high rates without exceeding supply. The geographic concentration of molybdenum at Climax Mine created strategic vulnerability for United States. If sabotage or accident had disabled the mine, American armor production would have faced immediate shortage. The mine was guarded, but was civilian facility, not military installation. Security was tighter after Pearl Harbor, but the mine remained accessible to workers without extensive security clearances. The vulnerability was recognized, but deemed acceptable given remoteness of location and difficulty of sabotaging underground mining operations. German intelligence was aware of Climax Mine's importance. Abwehr reports identified the mine as critical American strategic resource. Plans were discussed for sabotage operations using German agents in United States. The plans were never executed, infiltrating agents into United States, getting them to remote Colorado location, conducting sabotage in guarded mine, all without detection, was considered too difficult. The mine's isolation protected it more effectively than active security measures. The molybdenum supply influenced Allied armor tactics. American tank doctrine emphasized mobility and numerical superiority over armor thickness. Sherman tanks were designed to be fast, reliable, and producible in quantity. Armor was sufficient for protection against most threats at combat ranges, but not invulnerable. The molybdenum content allowed thinner armor to perform better than thickness alone suggested. This supported the doctrinal emphasis on mobility. Tanks did not need maximum armor thickness, because armor quality compensated partly for reduced thickness. German tank doctrine emphasized armor thickness and firepower. Panthers and Tigers had thick armor and powerful guns but were heavy, slow, and produced in limited numbers. The emphasis on thickness was partly compensating for metallurgical limitations. If German armor quality had matched American armor quality, German tanks could have been lighter for equivalent protection. The weight savings could have improved mobility, reduced mechanical stress, increased production numbers. The molybdenum shortage forced German tanks to be heavier than optimal design would have required. The metallurgical advantage was not decisive alone. Tank combat outcomes depend on multiple factors: crew training, tactical employment, numerical strength, supporting arms, terrain, logistics. But metallurgy mattered at the margin. When Sherman encountered Tiger, the Sherman was outmatched in armor thickness and gun power, but Sherman armor absorbed hits better than thickness suggested. When hits penetrated, Sherman crews survived more often because armor did not produce secondary fragments. The survival difference was partly molybdenum. Post-war analysis assessed molybdenum's strategic importance. The United States Strategic Bombing Survey examined German war economy and identified critical resource shortages that limited German military production. Molybdenum was listed as critical shortage that degraded German armor quality. The survey noted that if Germany had possessed adequate molybdenum, German armor could have been thinner for equivalent protection, reducing tank weight and improving mobility. The shortage forced design compromises that made German tanks less effective than they could have been. The irony was that molybdenum requirements were small. Armor plate needed only 0.25% molybdenum, 2.5 pounds per ton of steel. A Tiger tank with 25 tons of armor required approximately 60 pounds of molybdenum. Germany produced approximately 300 Tigers per month at peak production. Total molybdenum requirement was 18,000 pounds monthly, less than 1 day's production from Climax Mine. The strategic impact was disproportionate to the physical quantities involved. Small amounts of one element determined armor effectiveness for all combatants. The geological accident that placed the world's largest molybdenum deposit in Colorado benefited the United States by denying Germany access to the resource. If the deposit had been located in Germany or German-occupied territory, the strategic balance would have shifted. German tanks would have had superior armor metallurgy combined with superior armor thickness. Allied tanks would have faced German tanks with both quantitative and qualitative armor advantages. The location of one ore body influenced the effectiveness of thousands of tanks over 4 years of warfare. Climax Mine continued operating through the Cold War. Peak production occurred in the 1970s when molybdenum demand for steel alloys reached maximum levels. The mine closed in 1995 when molybdenum prices declined, reopened in 2012, and continues operating today at reduced levels. The tunnels extend over 10,000 feet deep into Bartlett Mountain. The ore body is mostly depleted, but remaining reserves continue providing molybdenum for industrial applications. The mine that determined World War II tank armor quality is now a modest industrial operation serving civilian markets. The metallurgical lesson from World War II was that strategic materials in small quantities can determine weapon effectiveness as decisively as large quantities of common materials. Steel production required millions of tons of iron ore, coal, limestone, but armor quality required a few thousand tons of molybdenum. The small quantity resource was as strategically important as the large quantity resources. The lesson applied to other materials: tungsten for armor-piercing rounds, chromium for stainless steel, platinum for catalytic converters. Modern warfare required access to entire periodic table, not just iron and carbon. The strategic geography lesson was that resource deposits determine military capabilities regardless of borders or ideology. The United States possessed molybdenum not through superior metallurgy or industrial planning, but through geological accident. Germany lacked molybdenum not through technological backwardness, but through geography. The accident of mineral deposits influenced military outcomes as decisively as battlefield tactics or industrial capacity. Geography was strategy. The final assessment was that molybdenum gave Allied tanks measurable metallurgical advantage that contributed to combat effectiveness. The advantage was not dramatic. Sherman tanks were not invulnerable, but Sherman armor performed better than thickness alone predicted. German armor performed worse than thickness suggested. The difference was chemistry, and the chemistry depended on access to one mine in Colorado producing one element that most people had never heard of, but that determined whether tank armor absorbed hits or shattered under impact. The mine at 10,500 feet elevation in the Rocky Mountains that produced 75% of the world's molybdenum and determined tank armor quality for all armies in World War II. The mountain that made Allied armor tougher and forced German armor to be thicker. The geological accident that became strategic advantage.